What if I told you creating tokens on Solana takes minutes, not days? Usually it involves complex and unfamiliar Rust code, long and tedious coding sessions, confusing documentation, especially difficult for a JavaScript developer. Gill solves exactly these problems. It's a lightweight JavaScript client for the Solana blockchain, designed to simplify the entire process of creating, minting, and managing tokens on Solana. In this course, I'll guide you step by step through the process of using Gill, demonstrating how it simplifies and streamlines your entire workflow. We'll start out with creating a brand new token with metadata, then we'll go on to actually minting tokens to a wallet that you either own or do not own, and then I'll demonstrate the process of actually transferring tokens to any wallet on the Solana blockchain. All in a matter of minutes, not days. No Rust required. If you get lost at any point during the video, you need to jump around. There's going to be timestamps in the description. Feel free to jump around and get back to any session you need to. All right, are you ready to simplify the token creation process? Let's jump in. Hi there, I'm Nick, and welcome to this video. I'm going to go through the basics of using the new JavaScript client to interact with the Solana blockchain. Specifically, we're going to go through using Gill, that's G-I-L-L. This is one variation of the new JavaScript clients that exist. It is fully compatible with Solana Web3.js or Solana Kit from Anza. It uses the same libraries under the hood, but let's go ahead and dive in. So you can see here on the README for Gill itself under the Solana Foundation's GitHub org, we have a fairly detailed README that describes a lot of the stuff we're going to go through in this video, but I'm just going to go through and explain everything. We're going to do the coding, and it's going to be awesome. So take a look at the README, and let's go ahead and dive into some code. So to start us out here, I have a very basic TypeScript Node.js repo sort of scaffolded out. The only thing that's in here right now is these dependencies, basically to use TypeScript and Node, as well as loading environment variables if you so choose to. And then we're actually just gonna code everything directly right now. So the first thing to do is actually installing Gill. Now I am actually gonna use pnpm as my package manager, but I'm gonna go ahead and install Gill. So pnpm add Gill. And it's gonna install my node modules, give me full TypeScript support, and now I have Gill version 0.2.0. At the time of this recording, this is the latest version. I actually just published this version yesterday. So it's still in beta, but it has a lot of additional functionality on top of Solana Kit and Solana Web3.js version 2, but still being compatible with it. So let's go ahead and dive into some code. The first thing that you're gonna wanna do when you're interacting with a lot of these things, especially if you're doing basic scripting like this, is you need some sort of key pair to actually sign transactions. So in my case, I'm actually going to be loading my local key pair on my file system. So I'm going to load in this nic6z address, and Gill has this amazing helper function to actually help you load key pairs in from your file system. So I'm going to create this signer. I'm going to call it signer, and I'm going to load it in using the load key pair from file. Key pair signer from file. There's two different types of key pairs that exist within the new JavaScript client. There's a key pair and a key pair signer. A key pair under the hood is just the web API crypto key pair from the standard crypto libraries. And then a key pair signer is one signer that is specific to using and interacting with the Solana blockchain using the new JavaScript client. It gives you some of the ED25519 cryptographic stuff built in, and it makes it so you can easily sign transactions and messages that are all compatible with the Solana blockchain. So now that we have our signer loaded in, it's actually just that easy to load a key pair from your file system. Specifically, this will actually load the default key pair from the Solana CLI, or if you want to pass in a specific file path in here as the value, you can also pass that in too. But since I just want my key pair from my file system using my local Solana CLI key pair, I'll go ahead and log this out to show you that it is in fact the same. So once you have a key pair signer, I'm just gonna keep calling them signers for short, you can call the address or the key pair. You can see it is a crypto key pair there. It also has a sign messages function and sign transactions, and we'll get to that later. So now that we actually have the signer, we can go ahead and log this out, and we can actually run all the scripts within this repo using ESRun. If you're not familiar with ESRun, it's this phenomenal lightweight JavaScript runner package that you can basically throw any JavaScript, TypeScript, CommonJS, ESM file at it, and it will just handle everything. It'll work no matter what. It's awesome. So you can always run npx esrun and then just pass it the file name. In this case, it's the script.ts. And you can see here that I did in fact load this exact same signer from my file system. And now the reason I'm doing this is because when you're interacting with the Solana blockchain, if you're using one of the public networks, you need Sol in it. In this case, I have DevNet Sol on this particular wallet. I am connected to the Solana DevNet here in my Solana CLI. So I have DevNet Sol, but if you wanted to connect to any other network, you can also do that. Speaking of which, actually connecting to the Solana network with the new JavaScript client, you can create a Solana client connection, getting access to your RPC methods and all of those things using the create Solana client function from the Gill SDK. And within this, you can actually pass in the URL or the moniker for any of the networks. If you wanted mainnet or if you wanted DevNet, you can pass in the actual string for them. And you will get a DevNet RPC connection here. So you can see if you hover over it, we have our RPC DevNet, and this has access to all of the Solana RPC API calls, so the RPC methods. And we can actually now just call these RPC methods directly within our code. So let's go ahead and do that. One of the most common RPC method calls that you're going to be using a lot is get latest block hash. Because the way that the Solana blockchain works, you need the latest block hash to include within your transaction. It's basically like a recent timestamp check that your code can actually submit with your transaction. So we need to actually get that from the blockchain. So in order to make RPC calls, we can call the RPC, use our RPC connection here, and you can see within our editor, we get auto completion within IntelliSense, and we can get the latest block hash. And then when you actually are ready to send this RPC call to your RPC server, in this case, we're using the public DevNet endpoint, you call the .send function. And then if you want any custom configuration information in here, like an abort signal using JavaScript abort signals, you can do that too. And since this is an async function, we can also get this value. To note, most of the things within the new JavaScript client does use async await, so you'll have to use promises and all that kind of stuff within JavaScript. Most devs are familiar with this at this point, but just to point that out. Once you get the response back from the blockchain itself, from your RPC connection, this is a pretty common syntax that you'll see in a lot of the examples. Because the way that these RPC methods work under the hood within the new JavaScript client, you actually just get a generic value key back, and this has the value that's actually returned. So using this JavaScript syntax, you can basically rename this value attribute to be called latest block hash or whatever attribute name you want to give it. So now our latest block hash is actually stored within this latest block hash variable. And just to show it out, we'll go ahead and log this. And if we go ahead and rerun our same script, you can see we've got our latest block hash directly from the blockchain. If I run this again, we'll get a different value. We can see our last valid block height has ticked up, and the blockchain is progressing along. So that's how to get a block hash. That's how to make any of the RPC calls to the blockchain itself. The next thing is actually creating transactions. The easiest way to create a transaction with the new client is actually using the create transaction function. Kind of makes sense. So we'll create a transaction. I'll call it TX, and I'll call the create, if I could type, create transaction. So we're going to call create transaction from the Gill SDK. And this takes in an object that wants all of these values, basically. So there's, notice how there's a question mark here. These are optional values that can be included within your transaction. Ultimately, these are highly recommended to be included. Latest block hash is ultimately required when you send your transaction, but let's go ahead and fill in this information. So the fee payer for this transaction is going to be my signer address. I'm going to pass in some instructions. We haven't created those yet, so I'm just going to give this an empty array. Next up is I'm going to give it a version. I'm not doing any address lookup tables here, so we're going to go ahead and make this a legacy transaction. I'll go ahead and reorder those. And now we have a valid transaction that we can continue processing, continue doing things on within our code, and ultimately send it to the blockchain. but our transaction doesn't do anything yet. We didn't give it any instructions. So let's go ahead and create our very first instruction. So the way that instructions work within the new JavaScript client is similar to how they work with Web3.js version 1. You still have the same information under the hood, but the way you actually create those transactions might look a little bit different. So within Gill, you can use any of the system program, the compute budget program, token 22, and the memo program. All of those are included within the Gill package. So if you install this one package, you get a single entry point to all of these compatible clients. So let's go ahead and create a simple instruction. This will be our memo instruction. This is sort of the simplest instruction you can possibly create on the Solana blockchain. And we can actually import the get add memo instruction function that's exported from Gill. And we can basically just give this just a plain memo string that we want to send to the chain. And we'll say GM world. And now we can just include this single transaction within we can include this single instruction within our transaction, and then we're almost ready to send this to the network. Let's go ahead and log this out just to show you what the structure of this transaction actually looks like. And we'll go ahead and rerun the same code. I'll go ahead and clear my terminal, rerun the same script, full screen this, and you can see we have, again, the same signer being loaded in. We have this transaction object. We have our latest block hash again. We'll ignore that for now. And our transaction object, we have our instructions, which is an array of instructions. We're interacting with the SPL memo program. We're giving it some data. This is automatically handled under the hood when you create instructions using these types of helper functions. It will properly format all the data that's required for that transaction. It does the proper encoding. It converts whatever input you put in there to a raw uint8 array, which can be sent over the wire. We have our transaction version. This can be legacy or version 1. We chose legacy. And then we have our fee payer information. And you can notice here that this fee payer, it's the same address. And we have our key payer, our signed message, and our signed transactions, because this fee payer, how we created it within this transaction, is a full signer. It has the ability to actually sign this transaction. Sometimes you might fall in the case where you just have an address because maybe you want your users, your customers, to be signing the transaction, paying the transaction fee. You can pass in the address itself. So if you just have the base 58 address, you can pass that in. And if you rerun this, you can see we have the address set as our fee payer, but it doesn't have any signing capabilities. So if you have a front-end application where users are connecting their wallet, Phantom, Backpack, Soulflare, whatever, they can then sign this transaction. They are the fee payer, and then you can send it to the network that way. But because we are going to be the signer here, we'll go back to this. And then the last thing we actually need to send this transaction is the latest block hash. So I'll go ahead and reorder this. And we'll go ahead and include our latest block hash inside of this transaction. And now our transaction is fully ready to be sent to the blockchain. So now that we actually have our transaction, we need to be able to send it to the blockchain. So how do we actually do that? Well, first of all, we need to sign the transaction, and then we can actually send it to the blockchain. So we can sign the transaction using, again, one of the functions that are within the Gill SDK and also within Web3.js version 2 or Solana Kit. I'm going to create a new variable called sign transaction. So we're going to go ahead and grab the function we need here, which is called sign transaction message with signer. There we go. I'm still learning all the new names myself too. And all we do with this is it's, again, an async function. So we need to await the promise, and we can pass it our transaction. And now we have a signed transaction. So let's go ahead and log this signed transaction out as well. We'll go ahead and rerun the script, and you can see our transaction from before it's signed looks exactly the same as before. Our fee payer has the ability to sign this transaction because it has signed transaction function. And our signed transaction actually looks different, because what this signed transaction actually is, it's all the message bytes and the actual signatures from our address, from our wallet, our signer, and our lifetime constraint, so our recent block hash. It's included all of this, so this is fully serialized, ready to send over the wire. So now that it's signed, we can actually send it to the blockchain. So how do we actually send a transaction to the blockchain once we have it signed? Well, we call send and confirm. So within the create Solana client function, it will not only return our RPC connection, but there's also the send and confirm transaction function, which we can, like you guessed it, we can await the promise for it, give it our signed transaction, and now we have our transaction. We can send it to the network and it's done. It's done. It's there. Our transaction will land, go through all the good stuff. Yay, blockchain. But what's our transaction signature? Like, how do we get that? There's a function for that. Once a transaction is actually signed, you can actually get the signature directly out of it. So actually, we'll say this. Let sig equals get signature from transaction. We'll give it our signed transaction. And we'll go ahead and log out our signed transaction, or rather our transaction signature. And if we go ahead and run this transaction, or run the script again, you can see the editor looks kind of like it hangs a little bit because it's actually sending the network request, and we have a transaction signature. Well, the cool thing about the Gill SDK is not only can you get the transaction signature before the transaction's actually sent because it's been signed once, that's just how Solana signatures work, but the send and confirm transaction function also returns the same signature. So we can also log it out a second time if we want, and if we resend the transaction, you can see that the transaction signature is the same on both because that's just how Solana transaction signatures work. Now, once you have a transaction signature, you might want to inspect this on the Explorer. Well, there's, you guessed it, a function for that. Inside of Gill, there is a get Explorer link function, and you can get the Explorer link for an address, a block, or a transaction. So since we already have our transaction signature, we can go ahead and say, this is our transaction signature, give us the full Explorer link. Now, by default, this function will give you the mainnet Explorer link, but if you look up here, we're actually connected to DevNet. So I'm actually going to create a constant, Solana cluster moniker, and I'm going to call it DevNet. And I'll go ahead and replace this in here. And then inside of get Explorer link, we can also pass in the cluster itself, and then get Explorer link will get us the correct Solana Explorer link, so explorer.solana.com, for whatever cluster you want. So mainnet, devnet, testnet, or even localhost. So if you are interacting on localhost using a local test validator, you can also use the Solana Explorer to view all that too. So we'll go ahead and log this out. Run the script again. You can see we now have this Explorer URL. It has the cluster devnet. So let's go ahead and open this. So if we pop over to the Explorer now, same URL that's loaded up, here's our same transaction signature. You can see all the typical Blockchain Explorer stuff. You can see we're connected to the DevNet over here. And if you look at the transaction information itself, we have our accounts, that Nick6Z, that was our signer, was the fee payer, signer, and writable. It has the memo program, and we have our single memo program instruction. It's there. We have our good old-fashioned GM world put inside the memo, and now GM world is on-chain on DevNet. But there's something you might notice about this transaction, and it's the fact that we don't have any priority fee or compute budget information already set for this transaction. We consumed some compute units, so we consumed about 4,200, almost 4,300. And the best way you can actually have success in landing your transactions on Solana is by setting your priority fee and setting your compute budget settings via these instructions within your transaction itself. And that's absolutely the best way you can get your transactions to be landing faster and landing more reliable. So how do you actually do that? Well, you have to add 2 instructions to your transaction itself. You could go through the process of manually adding them, manually crafting these, but with the create transaction function, you also, if we hover over it, well, kind of gives us the ellipsis. With the create transaction function, you can actually easily set these values, our compute unit limit and our compute unit price. So let's go ahead and set a compute unit limit. So we can go ahead and give it a value here. So our previous value was about 4,200. Sometimes you need to add an additional buffer on top of the compute units consumed. So we'll just go with 5,000, and we'll go ahead and run this again. You can see our transaction goes through, new signature. We'll pop back over to the Explorer. You can see we consumed a different amount this time, about 4,400. And you can see this transaction is actively being confirmed because this blockchain is actually that fast. So there we go. Now it's been finalized, reached maximum commitment level. And now we have an additional instruction within here. We set 5,000 CUs as our budget limit for this transaction. And that's it. It's that simple. You could do the exact same thing with your priority fees. So if you have a priority fee value, you can also set that here, our compute unit price. That's part of your priority fee. This is basically you set micro units per LAN port. So if we say, micro LAN ports per compute unit consumed. So if we are saying we're going to consume 5,000 as our maximum for this transaction, if we say we're going to pay 1,000 micro LAN ports per compute unit, we can send this transaction again. You can see we have a new Explorer link. Go ahead and open this up. Swap back over to the Explorer. Transactions being confirmed. We have, again, our value has changed here because we're doing more computation. We have the compute budget instructions. Now we have our compute unit limit, our compute unit price. We have fully set and fully optimized our transaction by including both of these instructions inside of it. So the last thing I want to show within the Gill SDK is debug mode. This is this nifty little feature that we put inside of the new JavaScript client here, and you can basically enable debug mode to help you as a developer debug your application, debug your transactions. So you can enable it in 3 different ways by setting the gill_debug environment variable. So if you have, you're using a serverless function or Vercel or, AWS, GCP, whatever, you can set an environment variable or even, node locally or bun locally, whatever. You can set this environment variable directly through your CI/CD and things like that. So if you have like your preview environment, you can enable debug mode within that preview staging environment. You can also set the global value or in window using the window object. So in your browser's console. So if you have a front-end application that's deployed, you're testing the actual application. Even if you're testing it on localhost, you or any of your users, so if you have an advanced user, they can enable debug mode within their console. So that way they can get some of this information because it's all public blockchain information anyway. And this can really, really help debugging applications on the front end. So we'll go ahead and enable debug mode here, and we'll turn on, we'll set this global environment variable within our code. And we'll go ahead and set this towards the top. It doesn't really matter where you set it, as long as you set it towards the top. Actually, if your editor is configured to support TypeScript, so we can actually see that we have this gill debug level and gill debug mode, or gill debug values. We can set these. We can set our desired debug level if we want. We'll enable debug mode by default globally for this entire script. If we run this again, go ahead and clear. We'll run the script again. And you can notice that in some places in the code, I think in this one, we just have this one example, we are enabling info debug mode by default. That's the default log level. And you'll see that you'll get these gill prefixed console logs just sprinkled throughout your code. This can really help with debugging. Right now, this one we just showed the transaction URL. Sort of not as helpful because we're already doing that within our code. But this can make it so you don't have to sprinkle console logs throughout your code. You can just turn on debug mode or turn off debug mode. The other one here is actually controlling your debug log level. So if we change this to include debug level of debug, the lowest level that is supported within the Gill SDK, we can run the script again, and we'll see how the output actually changes. Now there's 2 logs. We have the same one as before, because this is info. Info is sort of above debug. So if we enable debug, we'll see all the debug logs. And we also get the base 64 transaction logged out for you as the developer, or maybe your front-end dev, or your users if they really want to. They can get the base 64 transaction here. And the really cool thing about this is that you can copy this base 64 value. You can go to the Solana Explorer, switch back over to here, click on this inspector tab at the top. We can use the transaction inspector. We can paste in our base 64 transaction, and then we can just inspect this transaction, whether or not we sent it to the network. So maybe you have some sort of issue where your transactions are not landing, they're all failing, you can't figure it out. You can pull it up on the inspector here and view it like it's a block explorer, like it's a live transaction that actually went. You can simulate it, get all of our transaction outputs. You can check all the values. Oh, went back by accident. Simulate it, and you can see all the exact same information that you would expect to see on the Explorer for a transaction that actually was valid and sent to the network. And this is really cool. So if you have any error logs that you want to, or error messages that you're trying to debug, so let's say if we set our compute unit limit to a really low value, and we try to send this again, you can see, oh no, our transaction failed. For one, we have the logs that are displayed here just because we have this whole error message. But if you copy and paste this base64 transaction, go back over to the Explorer, and go back to the inspector, paste this in, you can see same information. Transaction appears to be valid, but if we simulate it, we can see sort of the pretty log output for trying to figure out what actually happened within the transaction. So this is a really, really nice troubleshooting tool that Gill ships with. So that's going to wrap it up for this video. I hope this was really helpful, giving you sort of a really quick crash course on the new Solana JavaScript client, or I guess the new JavaScript client for interacting with the Solana blockchain. Thanks. Catch you in the next one. Hi, I'm Nick, and in this video, I'm going to show you how to create tokens on Solana using the new JavaScript clients. Specifically, we're going to be using Gill in this example. You can do a lot of these similar things with Web3.js version 2 or Solana Kit, but Gill makes it a whole hell of a lot easier. So let's go ahead and dive into some code here. So much like the previous video, if you haven't already seen it, how to get started with the new JavaScript clients, we have Gill installed. We've updated from the last version. This is 0.4.0. The last video was 0.2. And we're just going to dive in and start writing some code. So the first thing you're going to need when you're building these transactions and sending them to the blockchain is you need a connection to the blockchain. So let's go ahead and create that. I'm going to create a Solana connection. So create Solana client. I'm going to import this directly from Gill, and I'm going to pass in my URL or moniker. And specifically, I'm going to be using DevNet for this. You can use any of the other clusters. The particular address that I'm going to be using for this this demo here is this NIC6Z address. And to show that it also has a balance, I'm going to get the balance on DevNet, and we have some DevNet sol available, so we can do all things that we would want to do with DevNet. So we're going to go ahead and grab our RPC and eventually the send and confirm transaction function, so we can actually, send and confirm the transaction later when we build it. But now that we have a connection to the blockchain, we can start building our actual transaction to create our token. This is going to come in a couple of different steps. The first thing we're going to need is we're going to need a signer. Now, since we're doing this all with the sort of CLI scripts and everything, we're just going to load a CLI our key pair signer from my local file system. I'm actually going to load this NIC6Z address directly from my file system. And in order to do that, Gill has a helper function to load files for our load key pair signers from the file system. So I'm going to load a signer. This is key pair signer from file. And by default, this is going to give us the exact same address and key pair that I've sort of displayed in the console there. So I'm going to go ahead and log this out too, just to show it. And signer.address. Just to show that this is the same exact address, we're going to use esrun to run these scripts, and I'm going to pass it in this file name, and you can see here we have the exact same NIC6Z address. So now that we have a signer, let's go ahead and start building our transaction. So I'm going to create a new transaction object. I'm going to call it TX for short, super common convention for creating transactions, and also same with IX for instructions. But we're going to call the create transaction function, and I'm struggling with typing today. But we're going to call create transaction that's again imported from Gill, and we can start use our IntelliSense here. We can see all of the values we can pass in, and we're just going to start passing in all of these required attributes. We'll start with the fee payer. Pretty typical thing when building transactions is they all need some sort of signer, whether it's a user's wallet from their Phantom, Backpack, Soulflare, or whatever, or if you have a key pair loaded from your local file system or from your backend server, you can load that in as well. Next up is going to be the version. I'm going to use a legacy version, so we're not using address lookup tables here, so we don't need a version 1 or a version 0 rather. The next thing is instructions. This is going to be an array, and this is actually how we're going to tell the blockchain all the information it needs in order to actually create our token. We're just going to leave this blank as an empty array here. And then the next thing is we're going to pass in this latest block hash. We don't actually have this latest block hash yet, but now that we have a connection to our RPC, we can get our latest block hash. So we're going to call rpc.getLatestBlockHash. And typing is apparently not my strong suit today, so I apologize there, but we're going to grab this latest block hash. We're going to destructure this and rename it. There we go. So now we have our latest block hash, and effectively we have a transaction that's sort of ready to be signed and sent to the blockchain, but it doesn't do anything yet. In fact, if you tried to send this, it would literally fail because there's no instructions. Every transaction is required to have some instructions in it. So let's go ahead and actually build our instructions that we need to actually create a token. So there's a couple of ways that you can create tokens on Solana. There's different programs you can use, and then different other programs you can use for metadata. So let's talk about that real quick. There's two primary token programs that exist. There's the SPL token program, sort of the original one. It's the legacy token program. And then there's the token extension program. This is the newer iteration, also from the engineers at Anza and from Solana Labs. And basically, these two programs, they're very identical in a lot of ways, but the token extension program has these idea of extensions that are built in natively within the program. So it sort of offers these different ways you can have customized logic without implementing that many new features yourself or creating a completely new token program. It sort of ships them easily and accessibly. For this first demo, I'm actually going to go through creating using the legacy token program. And sort of the two main caveats here that you have to think about is, one, the legacy token program does not support metadata by default internally within its own program. So we have to use a different program for metadata. And in this case, we're going to use Metaplex's token metadata program. Gill ships with the functionality inside of it to use Metaplex's token metadata program, so we can go ahead and use that. The other option is if we wanted to use the token extension program that has metadata functionality built into it in using the form of metadata pointers and the metadata extension, so we can actually have just a single program that controls both the metadata and the mint itself. But let's go ahead and use the original token program, since that's what most people are most used to. So in order to actually create our mint, we need a couple of instructions, and we can put all of these in the exact same transaction, which is really great. So the first thing we need to do is we need to sort of allocate our mint on chain. So we need to generate a new random address. So we'll call this mint, and we're going to generate a key pair signer. And so now that we have this key pair signer, we can log this out if we want to. And every time we run this, we'll just get a different address. We can run it once. We have a 13J, we have a EHB, whatever. It's completely randomly generated. And once we have this, we can actually tell the blockchain to allocate this account on chain. And the way we do that is with a system program instruction called get. It's called the create account instruction, but we can call it using get create account instruction, which is exported from Gill. And we can pass in all the information we need here. You can see we have the LAN ports, new accounts, the payer, program address, and the space. So the LAN ports is the total amount of space that we actually need to allocate this account on chain. And because this account is our token mint, we need to know how much space our token mint actually needs on chain. So there's a function for that. So we can calculate the total space that we need using a function that's exported from the SPL token package, or I guess the Solana program token package, which is also exported inside of Gill. So it's called get mint size. And this will give us the total mint size that we need for our transaction, this actual account that we're going to send for the mint itself. So now that we have the total space, in fact, we'll just put that in there because we need the space. And this will basically just calculate how much actual space we need to actually allocate on chain. Now that we have the amount of space, we can get the minimum balance for rent exemption. and we need to get it for the space that we're actually allocating on chain. Because the way that the Solana account model works is every single account has to have a minimum land port balance, a minimum SOL balance to keep that account alive in the Solana blockchain state. So now that we have that, we can pass in our new account. This is going to be our mint because this is the actual address that we're going to allocate on chain. Next up is going to be our payer, and this is going to be our signer. And let's see what else is here, and program address. So the program address here is the token program that we want to be the owner of this account. Accounts on Solana are owned by other programs. By default, they're owned by the system program. That's sort of a wallet account, if you think of it that way. So like this signer, this is a wallet account, if you will. Because this account that we're creating now is going to be our token mint, it needs to be owned by the token program. So because we are using the original token program, we're going to use token program address that's exported from gill. And now we have allocated our mint on chain. We've created the account. Now we need to tell the token program that this is a mint. It has to have the all the mint functionality inside of it. So the way we do that is another instruction, and we need to initialize our mint. So we're going to call the get initialize mint instruction. And this get initialize mint instruction takes in a whole bunch of parameters. And this is basically how you configure the token you're trying to create. So the first thing is our mint, because we already have that created. And this is actually just going to be an address. So I need mint.address here. And the next is the mint authority. Now, the mint authority is the actual address or signer that's required to sign transactions when you want to mint new tokens. So issuing new tokens to any wallet you want. They have to actually sign this. This is the authorizing key pair in order to actually sign these. After our signer, we can pass in a freeze authority if we want. By default, the freeze authority will be, we'll just set it to our signer.address again. So in the future, if we want to freeze this token or freeze the tokens that are owned by users for some various reasons, you can sign with this address, this freeze authority address. They can sort of freeze those tokens wherever they are. Next, we will say how many decimal places we want our token to have. Depending on whatever your use case for your token is, you might want to change this. 9 decimal places is a pretty common one. So if you think of some of the popular tokens on the network, like Bonk or WIF or anything like that, they typically have 9 decimal places. But if you think of a typical fiat currency, something like USD or euros, they typically have 2 decimal places is how many places that consumers actually see. They actually have technically more than that. And that's it. Now we have initialized our mint. So we could sign and send this transaction right now. And in fact, let's go ahead and do that. So we're going to sign our transaction. We're going to call the sign transaction message with signers function, pass in our transaction. And now we can actually sign and send this transaction to the blockchain. So we can send and confirm. We'll pass in our signed transaction. And in fact, I'll go ahead and log out the Explorer link here too, so we can sort of explore it and see how it actually looks. And then we'll point out what we're missing here for creating our token. You might have already guessed what we're missing. Now, because we're using DevNet for this, I'm going to log out the DevNet Explorer link, and this is going to be a transaction. So I'm going to call the get signature from transaction and pass in our sign transaction. So we'll go ahead and log this out. We can go ahead and minimize this, clear the console. We can run this script again. And this next one is going to fail for a very particular reason, is because I forgot to put in one particular piece of information. So we have created our account. We've initialized it. We've assigned this account to the legacy token program, and we're using this get initialize mint instruction, which within gill, this is by default using the token 22 program, so the token extension program. So we need to actually use the correct token program address here. So if we pass that in, say this mint is going to be owned by the legacy token program, now we can, we'll clear, we'll attempt this again, and the transaction goes through. We get our Explorer link for DevNet. We can go ahead and open this up, and you can see transaction is actively being confirmed now. You can see here in the URL bar, we're on DevNet, and the transaction goes through. We sent it from Nick6z. That's where we initially signed it from. This is our mint that we actually randomly generated and created. We created the account, we initialized the mint, and everything was successful. Great. But there's no metadata. Let's go ahead and look at this token. We have an unknown token. There's no information stored in here. There's no name, there's no title, description, there's no image, nothing like that. So let's go ahead and now add metadata to this token itself. So back within our code, the way we can add metadata, like I described earlier, is the metadata is added using the token metadata program because we're using the legacy token program right here. So we can use Metaplex's token metadata program, and we can actually add our metadata. So let's call the the instruction builder for this instruction. So we're gonna call get create metadata v3 instruction, because we're gonna use the token metadata v3 instructions. So it's really only one that we care about here. And we can just start passing in all of our information that we need here. And you can see there's a whole bunch of information here. We have this metadata object, which has is actually an address. We have some of this other information that's actually just passed in, right? So let's go ahead and start filling out all this information, and then I'll explain it as we go. The first thing, this collection details, this can actually be null because we don't really care about it. We're not creating a NFT collection or anything like that. So our token is not part of a collection, it's just a regular token. We have data, which actually has all of our metadata that we can pass in. I'll go ahead and leave this blank for now, and we'll pass in the rest of this information. Is mutable, we're gonna set this to true so we can actually change our metadata after the fact. And in order to change the metadata, you have to have an update authority. So the update authority is similar to the freeze authority or the mint authority. This signer must sign the transaction in order to modify the metadata in the future. And for this example, I'm also just gonna use my signer. Next up, we need our mint itself. So we'll pass that in. And I guess this mint needs to be a address instead of a signer. The metadata. So this metadata is actually, this metadata attribute here is actually a address. We need to derive an address for our metadata account. So we're gonna create a new variable, call it metadata, and we're gonna call the get token metadata address function. We're gonna pass in our mint, and this is gonna give us a metadata address that is actually gonna store all this information for us on chain. So it's gonna actually create a separate account, not our mint account, because the legacy token program doesn't understand the concept of metadata. So we create another account owned by the token metadata program that will actually contain all this information. And this is actually just gonna be the address of that account. And so we have the PDA that's derived using the correct derivation. And next up will be our mint authority. And because we already have it set up above, we'll pass in our address here, which actually this needs to be a signer. Next up is our payer. This is also gonna be our signer. And then we finally have our data. So our data is, again, all the actual metadata information that we want to be stored on chain. So when you look at an Explorer, you look at tokens in your wallet, this is what users are gonna see. So what should we put there? There's a bunch of information in here that we actually don't care about right now, because a lot of these are sort of for NFTs and things that are less fungible than a typical token. You have like a whole bunch of supply or whatever. So something like our seller fee basis points, we actually don't care about it because we're not gonna have seller fee basis points. Collection also, we don't care about collection because this is not part of a collection. Same thing with creators. There's no creators for this because this isn't an NFT. Same thing with uses, we can also ignore that. And now we can actually pass in the actual information we care about for our token, so the name. I'm gonna call this token Super Sweet Token. And next up, we can pass in a symbol, and I'm gonna call this SST. And the last thing we need is this URI. So this URI value is an off-chain URI for creating tokens. This is sort of off-chain metadata. Typically, this is a JSON file that you can pass in and actually have additional metadata get displayed. So how you get your image and all these types of things. That's actually how you get this. So for this example, I'm just going to grab a JSON file that is inside of the Solana developers GitHub org, and we'll open this up and show you what this actually looks like. So it has this JSON information in here, pretty standard stuff. We can zoom in some. It has an image URL that we can open if we want. And look, there's a pretty image, yay. And it has just this other information. This is the type of information that will actually get displayed when you mint your token. So now that we have this, we can sign and send this transaction. So let's go ahead and do that. Because now we'll create the transaction with our metadata, and our transaction goes through. We can open this up in the Explorer, switch up my screens here. Transactions being actively confirmed. We have this similar information. We have a different mint that we created because they're just different mints. We were randomly generating them. We have our metadata address, and you can see our transaction here was completely successful. We called 3 different programs. We have metadata program in here, and we can go ahead and open up our mint. Now we have our mint created. We have a title here, super sweet token. And we have similar information. We have 9 decimal places, we can refresh, and we have this token. And that's it. So we've now created our very first token on the Solana network using the token metadata and legacy token programs. So that was a lot of code in order to actually build this transaction, right? Like I got the secret. Gill has these transaction builders, which make it really easy to do all of this stuff that you want to do with like creating tokens. So all of this logic here, I would say probably everything from line 34 all the way down to 80. This is several functions we call and lots of stuff going on here. But I'm gonna show you the quickest and easiest way to actually create tokens on Solana. Are you ready for this? We'll call this TX2, and we're going to use the build, one of the transaction builders, and we're going to use the build create token transaction. This looks very similar to building a normal transaction. In fact, I'll even copy and paste some of this information here. So we'll grab a fee payer, we'll grab our transaction version, and we can start passing in all of this information that we need in order to create our token. We can pass in our metadata, so I'll just copy and paste this, get this actual metadata in here, and is mutable will be true. We can now pass in our mint, and there we go. We have almost the exact same thing. Now we'll pass in our latest block hash, and there we go. Now we have the exact same transaction that looks basically way simpler, right? Same metadata, same information. We're going to generate new ones. So we can go ahead and remove all of this code here. Get rid of this. We'll rename this to TX2, and we can, remove all these imports if we want. Clean up this code some. And boom. Now this file is way simpler. We can sign and send this again, and it's going to do the exact same thing. We'll switch over to the Explorer. We created a new mint, randomly generated. As this loads, we have super sweet token. We have 9 decimal places, all the exact same information we just did, except way easier. We created the metadata. We have all this information. And the way that under the hood, this create token transaction builder works is it just fully constructs the transaction for you, helps you set safe defaults. This will default to the token metadata program using the legacy token program. But if you want to use the token 22 program, token 22 program address, it's that simple. You can just switch the program, and now this transaction will be built actually quite differently, but it does the exact same thing. You create a token with metadata. So how do you actually mint some tokens? Well, check out the next video. And in this video, I'm going to show you how to actually mint tokens from a token that you've already created. This is a continuation of the previous video where I showed how to actually create a new token. This is actually how to mint them or issue them to your users. So let's go ahead and dive in. The thing to note here is we're using Gill, the new JavaScript client for the Solana blockchain. We're on version 0.4.0. And if you didn't already watch the previous video on how to actually create a token, definitely check that one out. It'll be linked up. Script's also in the same repo, but we're gonna assume you already have a token with mint authority and the signer for that mint authority. So let's go ahead and dive in. Just like anything you're doing with the blockchain is you need a connection to the blockchain. So I'm gonna create a new connection to the RPC. I'm gonna create Solana client. In this example, I'm gonna connect to DevNet. You can do all the same stuff on any of the other networks. I'm gonna grab the RPC and the send and confirm transaction. Next up, just like any other transaction, is we need to start building the transaction. And the first thing you need is a signer. So I'm gonna load a local key pair signer from my file system. So I'm gonna call load key pair signer from file. And I'm gonna go kind of fast through all of this because I've covered all of this information in some of the previous videos. So if you haven't seen those, check out the Gill crash course video. But we have a signer, and to show that this is also the same one that I'm using on my local file system, go ahead and log it out. And just for the sake of this, I'm also going to use ESRun, just like I've done in all the other previous videos. So I'm going to run npx ESRun, pass it in this script name, which is 3 mint tokens. And you can see we have this address. I can log out my CLI address as well. Same address, nick6z. And the reason I'm loading this address is because this particular address has DevNet Sol. We are on Solana DevNet here. I have DevNet Sol, that's the UD, that's URLD for DevNet. And I have DevNet Sol, so I can sign and send these transactions. So let's build our transaction. I'm gonna create a new transaction object, call it TX, very common convention for creating transactions. And I'm gonna call create transaction. I know, it's like rocket science. A lot of these names here, they're sort of set to help you figure out exactly what you're trying to do. So we're gonna start passing in all of this information that we need in order to actually create our transaction. None of this is particularly special here. We have a signer, we have our fee payer, which is a signer. We're gonna give this a legacy transaction version. We're not doing anything with address lookup tables, so we don't need a version 1 transaction. And now we have a almost functioning transaction. A couple of things here. One is that we don't have a latest block hash. So if you went to actually sign this transaction, it would fail because you don't have a latest block hash. So that's sort of the recent timestamp check that the Solana blockchain needs in order to actually do a lot of the transaction stuff. So let's go ahead and ask the blockchain for our recent block hash, that recent timestamp. So we're gonna call our RPC, get latest block hash, gonna call .send to actually fetch it. And we're gonna go ahead and destructure the returned value and give it a more helpful name, latest block hash. If I could spell. All right, so now we have this latest block hash. We'll go ahead and pass this into our transaction object as well. So we now have a transaction that's just about ready to be sent to the blockchain, except it doesn't do anything yet. Let's go ahead and do something. So what are we doing here? We're minting tokens. So we already have an assumption here that we have a token already created. This from the previous video, if you check back into the Solana Explorer on DevNet here, we created this token called Supersweet Token. It has a mint address of this HWZ or HWXZ. I'm gonna copy this address because we need to know the address that we're gonna mint tokens to. You can see here our current supply is 0. We have not minted any tokens to this address, to this mint itself. So we have a supply of 0. We have no tokens. Let's mint some. So I'm gonna go ahead and store this mint as an address in my code here. Go ahead and import address, give it this. So now we have our mint address. Let's go ahead and build our instructions to actually mint these tokens. And the way that tokens work on Solana is a couple of very nuanced things. One is you have your mint itself. This is sort of, if you think of like a national currency, the US Treasury Department, in my case in the US, or whatever institution is responsible for issuing currency from a country or a nation state, that's what we have. We have this mint already created. They have the ability to issue tokens to citizens and holders of your token. And the way that holders and wallets and users will actually own these tokens is called an associated token account. Basically, it's a way to link a user's wallet to the token mint itself using whichever token program they're using. So it's actually a PDA, program derived address, that's derived from the user's wallet, the token mint itself, and then the token program that the mint was created with. So we need to go ahead and create a user's ATA. And the user might already have an ATA, the associated token account already created, and you could fetch that from the blockchain and sort of check if they already have it. But there's actually a way better option. There's an instruction in the ATA program that will create the associated token account. It's called create associated token idempotent. And basically what it does is it will create the user's ATA, the wallet's ATA, if it does not already have it. But if it does already have it, it just continues on. It's sort of like a graceful failure. It just returns a success message. And this makes it so you can actually create the token account in like the best possible way. So let's go ahead and create this. Create associated token. There we go. Create associated token idempotent instruction. That's the one we want. And again, it's this idempotent instruction because it will create the account if it does not already exist. And if it does already exist, it will just continue on. So let's go ahead and start passing in all this information here. We need our mint, which we already know, this address up here. We need to know the owner. So this is going to be the actual owner that's going to own these tokens. And this is sort of the address that we are issuing these tokens to. So we're going to issue them directly to my signer itself. So we're going to use the signer as the mint authority because it is the mint authority based off the previous video. It's going to authorize minting of new tokens, issuing new tokens. It's going to issue these tokens to itself, basically. It's saying, I own these tokens now. So I'm going to just mint them to myself. So that's going to be the owner here. The next is going to be our payer. Because the payer needs to be a signer, we're going to pass in our signer. It has DevNet Sol in this case that's able to mint these tokens. You need to know the token program that you used for the token mint itself. In the previous example, this mint that we created here uses the legacy token program, so we're going to pass that in. And then the last thing we need here is the ATA. This is going to be an address that we need to derive based off that information. So let's go ahead and create this. So const ATA equals await. We're going to get the associated token address. And you can see if we hover over here, we need to pass in a couple of pieces of information. We need the mint itself. We know that. We need to know the owner, so the actual owner of these tokens, in this case, my signer address, and then the token program itself. You can see here in the notes, this will default to the legacy token program, but we'll be explicit. We'll go ahead and pass these in. So we're going to pass in the mint. The owner is going to be our signer, and the token program is our token program. So we now have built our full transaction to we've created part of our transaction, our full instruction in order to create our ATA. So now that we create the ATA, we've allocated it on chain, has all the correct values and settings. We need to actually issue tokens to this ATA. So how do we do that? We need to get the mint instruction, the mint2 instruction, I should say. And we'll pass in the information here. And we can see if we hover over our type completion, we can just start passing in all this information. We have the mint, we know that. The mint authority, this is our signer that needs to sign this transaction because again, when we created this mint, this signer is the mint authority. If you look back at our code here, this is the simplified version of it. The fee payer here is set to the authority. Next up is we need to know the token address itself. This is going to be our ATA. And then the amount. How many tokens do we want to actually issue to our user's wallet address, this signer.address? Well, you can issue however many you want. So you can issue 10 as your amount, you can do 100,000 as your amount, it doesn't matter. The thing to note here is that this amount value, you need to take into account the decimal places of the token that was created. The token we created, I'll even put it here, the token that we created has decimals of 9. So if we were to issue mint to use this mint2 instruction to issue this amount. This would be, how many would this be? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is how many tokens we would actually mint to this user's wallet. So you need to keep that in mind of however many tokens you want to actually issue. So we'll go ahead and mint a whole bunch of tokens. I'll throw some, a little bit of pretty print in here. So we're going to issue 100 million of our token, but our token has decimal places of 9. So we're actually only minting 1.0 of the tokens themselves, if that makes sense. So now that we have this, the last bit of information we need is we need to tell it which token program that we're going to use. We're going to pass in our program address, token program. So we're going to call our idempotent instruction here, create the ATA if the user does not already have it. We're going to mint to that ATA, and all of this is using the original legacy token program. So we have now successfully and completely built our transaction to actually mint tokens to this user's wallet. In fact, I'm going to go ahead and call this here just to clean this up a little bit, make this a little bit more clear that this is the address we're going to mint to, this owner, because I'll show you how to actually change this to another address. Because right now, this signer is already signing this transaction. It doesn't need to sign this transaction if it's going to be the destination for these tokens, because we're minting to this owner destination. It doesn't have to sign, it just happens to be in this case. So let's go ahead and actually sign the transaction. We're going to call the sign transaction message with signers, give it our transaction, and we'll go ahead and grab this Explorer link. This is actually all the same, so I'll just copy and paste this. I'm going to take a shortcut. We'll get an import Explorer link. We will get our transaction signature. So we're going to log out this transaction. We sign the transaction because we have a fee payer. This fee payer also happens to be our mint authority, so they're going to sign it here. We're going to log out our Explorer link, and then we're going to send this transaction to the blockchain. So let's go ahead and do it. I will go ahead and clear my console. We're going to run this number 3 script again. So it goes through, and it's done. We'll go ahead and switch over to the Explorer. We'll open this up, and you can see we have signed it. We have our user's ATA was created, this CCMC. We have the mint, this HWX. We can now see that we have minted 0.1 of our SST token, our super sweet token. We created the user's wallet address, and because they didn't already have it, and then you can see this did some CPI calls to actually create the correct address for the user, the correct ATA. And then we called mint2, and we minted 0.1 of our tokens. You can see all the logs and everything directly here on the Explorer, and we're done, right? So we minted this token. Let's go ahead and refresh our tokens mint itself, and you can see we now have our current supply has gone up by 0.1 because we minted 0.1. We issued 0.1 of our tokens to an address. That's pretty cool. So a couple things here. One is this account, this ATA was created automatically for the user. Phenomenal user experience. That's like the gold standard of how you should create tokens, right? Or how you should mint tokens. This consumed quite a bit of compute. You can see here this was almost 28,000 CUs. Because we created the ATA, it didn't already exist, and we only minted 0.1 tokens. So let's run this transaction again. We'll actually mint even more. We'll mint even more tokens, and that's all we're going to change. We're going to just mint more tokens. We'll run this exact same transaction again, or the exact same script, get a different transaction, goes through, and you can see here our compute units have gone down substantially because this idempotent instruction, it didn't have to execute a bunch of logic, so it didn't have to do a bunch of computation on chain because the ATA already exists. We've now minted an additional 1.1 of our tokens, and it's much more efficient of a transaction. And if we go back to our mint again, we can refresh, and now we have 1.1 of our token actually created. And we can keep running this script as much as we want, and it's just going to keep doing the exact same thing, creating a transaction and minting tokens. So that's how simple it is. But it's kind of complicated here, right? Like, we're minting tokens. This is fairly complicated. There's a lot of stuff in here. We can change this address if we want to change the address of where we want to mint these tokens to. So I'll go ahead and grab a different address to also show this. We will mint to a different address or different owner. And so we're going to mint to this nicktr. And if you notice that my signer is nick6z, I have a bunch of vanity addresses because I'm a nerd. And so nick6z is our signer. nicktr is going to be the owner. We can run this transaction again. It's going to go through pretty similar as before. Pull this over, open up in the wrong tab. And the transaction goes through. We created the new ATA for nicktr because it did not exist. nick6z paid for the transaction itself, for the account creation. And now all of these wallet addresses have more tokens. So now there's 2 holders of our tokens. See here, if we go to the transfers, we don't have any transfers. We can see our metadata here of the information that we've posted about this token. And there we go. We've now minted tokens. But this does look a little complicated, right? So we can actually simplify this with the use of Gill's transaction builders. So Gill ships transaction builders for a bunch of common functionality. So I'm gonna create a new transaction and I'm gonna use the transaction builder. So we're gonna simplify this. This is, how many lines of code is this? This is 68 lines of code with prettier to make it print. Got a bunch of imports up here. We're gonna simplify this a whole bunch and we're gonna call the build mint token transaction. And much like as we did at the very end of the last video, we're gonna start passing in all this information for this transaction itself. We'll grab sort of the base transaction information. And we're gonna say the amount is, again, we'll do, was it 1 billion? So that's how many tokens we're gonna mint. The destination is gonna be our owner. The mint, we're gonna pass that in. The mint authority is our signer. And there we go. This is the exact same functionality we just did. So we'll go ahead and delete this, delete that, or rename that. We can delete this. And now we can remove these imports, remove this import. And now we're down to 44 lines of code and it's a lot easier to read. We are minting tokens from our signer, our mint authority signs it, pays the transaction fee, and we send it to the blockchain. We can run the script again. Go ahead and open this up on the Explorer. Transactions going through, it's still confirming because Solana's that fast. We have minted more tokens to this same exact address, the nicktr. We now own 2 SST tokens. And if we go back to our mint, go back to our mint overview, refresh the page, and just like you would expect, we now have our information displayed. Our supply has gone up. And that's how simple it can be to actually create a token and how to mint tokens to another wallet address. But what if you already have tokens minted and you're not the mint authority? Maybe you just own some of these tokens. How do you actually transfer them to another address? Well, I'm gonna save that for the next video. So go ahead and jump over to that one and we'll talk about transferring tokens. Hi, I'm Nick, and in this video, I'm gonna show you how to transfer tokens from one Solana wallet to another. We're gonna use the new JavaScript client called Gill, and let's dive into some code. So very similar to the previous video on how to actually mint tokens from a token mint, and then also creating them, we showed that in the previous video, we're gonna transfer tokens. This functions the exact same way almost. We basically only have to swap out one single instruction. And also to note here is that we already have a token. We'll go back over to the Solana Explorer. We have this token called Super Sweet Token. It's on DevNet, it's not a real token. And it has this mint address called HWX, and it has a bunch of supply has been minted. This is owned by a couple of random DevNet wallets, and we can actually transfer them from our signer wallet that we have and transfer it to any wallet that we want. And to note here is that the particular wallet, the signer I'm going to use is this nick6z. This is my Solana CLI wallet. We have a bunch of tokens minted to it, and we're going to transfer them. We're going to send them to another wallet. So I'll go ahead and sort of save this mint address in here as well. So because this is what we're going to need. And once we know the mint that we're going to send to, is we can start building our transaction. We can get our connection to the blockchain and actually build our transaction. So let's create a Solana client. And since this token exists on DevNet, we're going to go ahead and connect on DevNet. We're going to get our RPC and our send and confirm transaction. And then we can start building our transaction. Just like all the other times we've built these transactions, we're going to call create transaction directly from the gill SDK. And we can start passing in all this information. We need a key pair signer in order to actually sign this transaction. So let's go ahead and load in our key pair signer from our local file system. So load signer, if I could type, load signer from file. This is going to get our default CLI key pair. So if you can see here in my console, my address is nic6z. I have devnet sol. This UD is for devnet. And this is the address we're going to load in. So we're going to use that as our fee payer. Next up, we can set a transaction version. Again, because we're not using address lookup tables in these examples, we don't need a version 0 transaction, so we can use legacy. And then we can pass in an array of instructions and our latest block hash. But we don't have a latest block hash, so let's get our latest block hash. Just like all the other examples, as you start to do a lot of Solana development, you recognize all these patterns as you're doing the exact same things over and over, and getting a block hash is one of those things. So we're going to destructure this and rename it to latest block hash, make it a little bit cleaner. And now we have our core base transaction. We're ready to actually tell this transaction what we want to do. So what do we want to do here? Much like when we created our tokens, when we minted our tokens, we had two instructions. We have our create associated token idempotent instruction, and then we have our mint2. We're going to use this exact same create idempotent instruction. And this is, again, like sort of the gold standard for token operations on Solana, because the way this idempotent instruction works, we'll go ahead and just copy and paste it in here. So the way that this creates associated token idempotent instruction works, and this is sort of the gold standard for interacting with tokens, if you're minting tokens or transferring tokens. And what this does is, because of the way that tokens work on Solana, they have this associated token account model where a wallet, so the owner of tokens, actually owns an associated token account. And this is associated with a mint and a token program. And this is basically just how token ownership works on Solana. So when you issue tokens to a user or to a wallet, it's issued to their ATA, which is owned by their wallet. It's sort of this unique relationship. It has a lot of benefits, and it's got some nuances around it. But what this idempotent instruction here does is, if the user already has their associated token account, the ATA already created, it's not going to create it again. They already have it. So the transaction can be faster and cheaper. If they do not already have it, it will automatically create it for them. So the transaction is going to be a little bit more expensive, both in compute and in fees and rent, but they have to have this. So this is sort of the gold standard. Sort of think of this as like a graceful failure, where if they have it, it's going to continue on. If they don't have it, the ATA, it's going to create it for them and then continue on. So we are going to call this instruction, and we need to get the ATA for our particular owner. The owner we're going to have here, we're going to go ahead and transfer it to a random address. And this address, I have this totally random address saved in another file from another script. I think this was just like a randomly generated one. I don't even know what this address is, but it doesn't matter because you can send them to any destination. So this is going to be our destination. We need to know what token program our mint was created with. Okay, close that. This particular mint, this HWX, was created on the legacy token program. So you need to know that, and you need to use that correct token program. We're going to derive our associated token address, which is basically the actual address, again, that owns the tokens. And the way that you derive this, there's a helper function inside of gill for it. You need to know the mint itself, the owner, so the destination for these tokens, and the token program itself. And you can just pass all those in, derive the ATA, and then we have all the information to create our instruction now. So now this transaction will create the ATA for the user if they don't already have it, and if they do, it's gonna exit successfully. So now that we've created the ATA, the user has their destination for these tokens on our mint, or for our mint. Now we can actually transfer tokens to them. So we'll call get transfer instruction. And we can start passing in all the information that we need for this transfer instruction. We can pass in the source itself. Now the source is actually going to be the source ATA. So we're going to go ahead and derive this again. So the source ATA is because we're sending tokens from one wallet address to another. So we're going to be sending from my CLI wallet, this NIC6Z, to this 7S address. The source is going to be my local address itself. So I need this address. I'll go ahead and copy this in. So now that we have our source address, this is going to be here. So that's all we have to change there. So now we have the source ATA. So we'll pass in the source ATA here. The authority is the actual transfer authority for this particular token account. Because these tokens are owned by my signer here, I'm going to pass in my signer.address as my authority. Oh, sorry, that should actually be the signer, because this is required to sign this transaction, because you have to authorize transfer from the source ATA to the destination ATA. And then we can pass in our destination is our ATA itself, the amount of tokens we want to transfer. So we will transfer, we'll say 1 million of these tokens, 1 million amount. And to note here, this amount is based on the total decimal places for the token's mint itself. So if we look at the source code for when we created our token mint, you can see here we had decimal places of 9. So because we have 9 decimal places, when we're actually transferring tokens, the decimal places are going to be taken into account here. So 9 decimal places, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So effectively, this transaction is going to mint transfer 0.001 of our tokens. So that's how many tokens is going to be. The last thing we need is to know the token program that this is part of. So we're going to pass in the program address, token program address. And there we go. These are the only 2 instructions that you need to actually transfer tokens. You need to create an ATA if the destination doesn't already have it. So that's going to be our owner. And then you need to actually transfer from your source ATA, authorized by the source ATA's authority. In this case, that's our signer. And then the destination ATA, so the ultimate end owner destination, total amount, taking into account the decimal places, and then the correct token program that all of this token is owned by, is sort of managed by. This token mint was created using the legacy token program. That's this one here. So we need to make sure we pass that in. And I'm going to go ahead and just take the lazy approach here. I'm going to copy and paste this transaction sending. So we're going to sign our transaction. We're going to log out our Explorer link for it. And that way we can easily pull it up. And then we will go ahead and send the transaction to the blockchain itself. So clear our console. We'll run esrun. We'll use esrun to actually run the script. This one is called for.token transfer. So we can run this. Transaction goes through. You can see it's there's a little console hang here. That's because it's still processing the transaction. Probably got a little bit of rate limit. Been setting a lot of DevNet transactions lately. So there we go. Now we've transferred tokens from our source account to our destination account. So we transferred from NIC6Z to that 7S wallet address. You can see our balances have changed. We had both of these have the same token mint, the HW. We generated the ATAs, or rather we derived the ATAs for the source and the destination. We sent in, and if you look at the transaction instructions themselves, we created the ATA using the idempotent instruction, and then we transferred from our authority, signed it, NIC6Z, from our destination, or to our destination from our source. So this was owned by NIC6Z, and this is owned by the destination wallet. Now we can continue to send this exact same function here, or call this exact same script to send tokens from one wallet to the other. We send it a whole bunch of times. And if we pop back over to the Explorer, we can keep doing it unlimited times. You can notice that if we go ahead and refresh our mint itself isn't changing because we're not creating new tokens. But if we look at the total balance of the owner that we were sending from, so the NIC6Z, if we refresh this, you can see our balance has gone down and it just keeps slowly going down every time we send. We're only sending a very, very small amount, so it's not going down much in this example, but you can send as many tokens as you want. and you can keep sending those transactions. So much like I described in the previous two videos, this sort of has a lot of code. There's a lot of nuances you have to think about, but you don't have to if you don't want to. There is a transaction builder that Gill has. So we can call the build transfer token transaction, and we can use the transaction builder to actually simplify all this information that we're sending. So we'll grab our common information, so our signer, our block hash, our transaction type. We can tell it the amount of tokens we want to send. We'll send the same amount as before. The authority is going to be our signer, and the destination is going to be the owner, because that's where we're actually sending the tokens. And then we need our mint. So now this single transaction builder has the exact same functionality. It actually has a little bit more functionality than this previous one. So we can get rid of those. We can remove these imports because we don't need them anymore. The source address is going to be automatically derived. If you need to manually derive it though, you can pass it in, the source ATA, but it will automatically derive it for most cases. And then we can now remove these imports, and we can remove this one. And now this entire script is a lot simpler. It's a lot cleaner, easier to read, and it has almost the exact same functionality. It actually has slightly more functionality. So if we send this transaction now, I'll show you how this is actually different. We'll go ahead and pull this up. And if we look at the previous transaction, we had two instructions. So we had two instructions here. We had the create idempotent instruction, has a bunch of inner instructions because it did CPI. We have the token transfer instruction, and that's it. We have 1 and 2 instructions. If we look at the builder transaction that we used, it actually has more instructions. It automatically sets a compute unit limit, and it does the exact same thing with our idempotent and our transfer. So it actually has 3 instructions inside of it. Because of the transaction builders that Gill has, they actually all ship a recommended default that's sort of a safe default for doing these types of operations, to make it so your transactions are sort of default optimized, so you have a higher likelihood of them landing faster and being more successful. So that's going to wrap it for this video. If you want to learn any other things about using the new Solana JavaScript clients, leave it in the description, and I'll catch you in the next one.